Welcome to the Santa Barbara Astronomical Unit's monthly meeting for November. We have a few announcements and a commercial, and then we will introduce our speaker for the evening. Oh, thank you. That's a little too much. Okay. So where was I? Oh, yes. We have a commercial announcement from Pat Ph.D. See, do you want the long pause while I figure out the name, or do you mind?
Maria, next slide.
Okay. Pat McPartland, who is our merch manager. Okay.
Maria, next slide.
And, all right, well, my screen will come up. Thank you, Jerry.
One more slide, Maria.
My name is Pat McPartland, and I am the club's merchandise manager. And like Jerry was saying, this is a commercial. I sell branded club items, as you can see on the screen. We have mugs, patches, shirts, tote bags, blankets, and all sorts of goodies. And also the sweatshirts, which are going to come in handy when the Santa Barbara temperature finally goes below 75. So you can find this on our website under store. I don't ship, so I'll meet you someplace in Santa Barbara if you're interested. Just send me an email at merchmgr@sbau.org, and we can negotiate. So there you go. And back to you.
Thank you. And our speaker will be receiving the coveted SBAU coffee mug after the talk. So next up is Chuck McPartland giving a discussion or a rundown on our outreach for November, one of which we had last night.
Okay, thanks, Jerry. Okay, outreach-wise, boy, I better stay away from that thing. I wanted to say thank you to everybody who came out and helped out with the eclipse event out there at the Big Box. We had over 2,000 people show up, so it was a bit of a mob scene. Nice to see that we had lots of people come out for that. We also had a good turnout last night for Monte Vista School. We had 5 scopes, so that's pretty helpful. An announcement from Rebecca, the museum, the volunteer coordinator, is the museum needs planetarium volunteers to do weekday shows on Wednesdays and Thursdays coming up. And if you've been in the planetarium, you can see how cool that is. So you can contact Rebecca Coulter here at the museum and arrange to learn how to use the planetarium if you want to. It's a blast. And also, if you want to join in the outreach at schools and things, you have to go through Rebecca and get vetted that you're not a terrorist or some kind of criminal. So anyway, so school events are ramping up. We had a school event last night, and coming up on Thursday. That was last night. Wednesday night, the 8th, we have telescopes for Santa Barbara Community Academy over there at the Cumbre Junior High building there on Puerto. They're kind of on the back part of it. Then on Saturday the 11th, second Saturday of every month, is the monthly public star party. Okay, good. I'm forgetting to say slides. Right here at Palmer Observatory, starting at 7. We're starting a little earlier now that it's dark earlier. And then Thursday the 16th, Hope School. We'll have a telescope night for them. Friday the 17th, third Friday of every month, is our monthly public telescope night at Westmont. That's pretty cool. And for this one, volunteers are invited to come to a public music concert that they're going to have in the Dean Chapel, which is near the entrance. It's a little far away from the observatory, but you can go there at 7 p.m. for the choral pieces, even though that's when the observing starts. But anyway, you can mix and match. And then on Saturday the 18th, there's a star party up near Santa Maria at the Los Flores Ranch Park. And the entrance is a little bit away from their main entrance, that's a fairly dark site up there. A little bit of a drive, but worth it for a dark sky. Pardon me?
Also tomorrow. We have a luncheon in
Oh, well, that's for volunteers who have come out with telescopes and things, yes. But that's not really an outreach then. Okay, and then on Tuesday the 28th, fourth Tuesday of the month for this year, Telescope Tuesday at Community Rail Marketplace. We try to make sure we have a moon to look at. So it's fourth Tuesday of the month for November and December, but then for next year we're going to switch to the second Tuesday of the month. And then Thursday the 29th, Foothill School, it's their science night. And pizza and water for volunteers. At least it's not bread and water or bubble gum and water like we've had some of that. And also, we have some cross-pollination going on. The Science and Engineering Council is advertising our events, and they are also advertising other science events around town. So coming up on November 8th, 5:30 to 7:30 p.m. at Ventec, which I assume is some high-tech corporate group in town here.
It used to be the MIT Forum.
Used to be the MIT Forum. Okay, you're familiar with it. They're going to have a talk on the James Webb Space Telescope from 5:30 to 7:30 p.m. on November 8th. And then on November 9th, it's Las Cumbres Observatory's Astronomy on Tap at M Special down on State Street. And their bid is on what's lurking inside infrared dark clouds and talking about searching for exoplanets, I guess, too, inside infrared dark clouds. So that is outreach. Thank you. Oh, and we have member forums here and all kinds of propaganda. So if you're in a paper, we have star maps and moon maps and webpage listings and all kinds of stuff like that. So thank you.
Thank you, Jeff. And now we have the Vice President of the club, Ron Heron, formerly known as the Baron Ron Heron on radio. And he's going to introduce Professor Povich.
Thank you, Jerry.
Plus make a few announcements of my own. Number one, that was a good video that we saw on the ceiling, wasn't it? How come I don't see anything that good on YouTube? A lot of crap on YouTube along with some Neil deGrasse Tyson. Listen, I'll get to it as fast as I can because we got a good talker, a good speaker all the way from Cal Poly Pomona. Welcome folks in. I just really want to do something that people in the club love when I started doing this. Raise your hand if you're totally new. Never come before. Raise your hand. Okay, how do we get you to keep coming? If you're a confirmed long-term member like my friend Mike Hardwick, raise your hand. There's more new people than old people. Well, we're all old. Anyway, I want to plug our blog. It's about to do its 142nd Monday morning 11 to noon program that you can watch if you go to YouTube and log in, SBAU Astro Hour. And we have a lot of fun. We don't have a huge crowd watching, but over time we've tallied up about 100 folks on an average that rotate. And all those shows are in there, and we cover it all. I like to think of the Astro Hour every Monday morning as like a free 1-hour course out at Broida Hall at UCSB in physics. Because I'm sitting there as the MC with the other talking heads on the screen from the club and the board, some of the most intelligent, outgoing, incredible men I've ever met. And what am I doing among them? I get to ask the silly questions. No more pizza at our meetings, and next Saturday's meeting is not happening, I guess. Whew. I was going to have to run that one because I guess President Jerry is going to a wedding. So watch number 142. When it comes March of next year, we'll hit our 3rd year. And very few of us have missed any of these Monday morning get-togethers. And we all have cartoons at the beginning, silly science cartoons will hook you, that Jerry forwards to us at least half a dozen every week. And then we run them down, and some of them are just knee slappers, let me tell you. Next month, our yearly, and this will be the first one we've had really using people in the club. We call it the in-house presentations open to SBAU members, where people that have a specialty or something they'd like to talk about get to fill an hour. We got 3 of them, 2 of whom are here tonight. Mike is going to end the program with some of the most beautiful shots he's taken on his telescope of the cosmos through his son's backyard telescope. You own 6, don't you? We'll start the show with Dave Feinberg's meteorite special for 20 minutes. Dave, raise your hand so everybody knows you. And then a gentleman who rarely makes it over, but I think he may be watching us on YouTube right now. He lives in Ojai, our only Ojai member, Rex Meach and his wife Susie. He's going to be the middle program of those 3 talks about navigating by the stars or sextants and things like that. He's done that in his younger years. Now the big story next month, December 1st, is the first real election we will have had at Santa Barbara Astronomical Unit in years. And Jerry and I thought we had it nailed down where we didn't have to worry about it anymore, but now we got to worry about it. Everybody's going to throw their hat in the ring, I'm sure. There's 4, I wrote some notes down, 4 offices up for grab: president, vice president, although we're running or we're willing to keep our jobs if you vote us out. If you want to run against us, fine, no problem. Secretary, we have 1 person who is running, and his name is Andy Allen. Andy, raise your hand. He's taking notes already. He's been on the screen with us, and that's currently being done by the McPartlands very well, I might add. Tessa, are you here, Tessa? Tessa! Can't wait, you're going to be there someday in the future. You're not going to run, I guess, this year. Okay. Keep hanging in there. And treasurer, Colin Taylor is stepping down. So I believe somebody is running for that. That would be Mrs. McPartland, who I just know you're going to have a lot of competition. Everybody wants that job. It's going to be awesome. But we'll see. What we'll do is, if you like to run, let me know. Get in contact with me. Check SBAU.org. Get my phone number or, well, my email address. Contact me. And we'll definitely run your name by everybody for a vote by hand in here next month on the 1st, as well as somehow online. I'm not sure who's watching us, but this program tonight, before I introduce the speaker, you'll know that it's all being sent out on Zoom. So get your campaigns ready, and we'll see if we have an all-new board. I'm there for booking the guests, and the treasurer does a lot of work, and nobody does more work than those McPartlands, I'm going to tell you right now. So, bring your hands for that, for the vote next month when we have our 3 in-house speakers, do 20 minutes each. And what have I forgotten? I think, okay, let's meet the man. It's going to be just as good a show as what we saw in the planetarium. Something about citizens helping out. It's sort of like SETI, but not exactly like. Joining the faculty of the Department of Physics and Astronomy at Cal Poly Pomona in the fall of 2012. I think I can read my writing. This man's an observational astronomer specializing in multi-wavelength observations, primarily infrared and X-ray, and that's modeling to study large-scale star-forming complexes in our Milky Way. Matthew received his A.B. in astronomy and astrophysics from Harvard back in 2000. After graduating, he served as a Peace Corps volunteer, math and physics teacher at Moshi Technical Secondary School in Kilimanjaro, Africa, Tanzania. That was 2 years, 2000 to 2002, 3 years. He attended graduate school at the University of Wisconsin at Madison, earning his MS in astronomy with a minor in physics in 2006 and his Ph.D. in astronomy in 2009. He further developed his research, education, and public outreach experience as an NSF Astronomy and Astrophysics postdoctoral fellow at the Pennsylvania State University, 2009 to 2012. Sounds qualified to me. Let's welcome him, shall we, to Santa Barbara, Dr. Matthew S. Povich from Cal Poly Pomona.
thank you so much, Ron, and thank you everyone for coming here and inviting me. And let's see how. Yes, that's my talk showing up there. I guess I don't really have much to add to that to that introduction. I think this club seems amazing and active. And if I did not live to a 2.5 and 3 hour drive away, I would most definitely want to join. Maybe I should anyway. Santa Barbara is really nice. I could use some excuses to come here more often. But alas, I teach at Cal Poly Pomona, which is far away from here. Probably a thing that's worth pointing out, as many of you may know, is that Cal Poly is part of the Cal State system, which means we are primarily undergraduate university. Unlike UC Santa Barbara, we don't have a graduate program with Ph.D. students. So the research that I'm going to talk about tonight is 100% done by undergraduate students who nevertheless were very talented and able to produce at times publishable work in terms of actual papers and journals and things like that. And in addition to the research, one of the things that I love doing is this, like coming and talking to people who are not necessarily professionals or students of astronomy or professional students of astronomy. I haven't been to a large number of clubs like this. I've been to maybe 2 or 3 over the years. And most of my experience is actually talking in schools, K through 12. I actually founded a program that we call BUILD. I even made this logo myself. I'm very proud of it. Bringing the universe into LA districts. That's still ongoing. We still, well, COVID, of course, put the kibosh on it for a while, but we started up again and been to 2 or 3 schools over the past year. One of my colleagues has taken over leading it for me, so I don't have to do it all myself. This is a picture of our dearly departed Pointy building, former landmark at Cal Poly. I love this picture. I took it during an eclipse party. We set up telescopes. This was, I think, the 2015 lunar eclipse. And so while my students were running the telescopes for 200 people to look at, I took exposures 6 minutes apart of the total eclipse moon rising behind our iconic building, and had a heck of a time compositing the Photoshop because of all the clouds in the background. It was kind of a pain, but even though the building's gone, I like to use this as kind of our old logo for Cal Poly Astronomy. Right, so tonight, I shortened my talk title just a Milky Way citizen science, although I can explain what taking the pulse means a little later. I do appreciate that it's hard to follow the wonderful planetarium show, but it actually saved me a lot of trouble because I thought about talking about that whole story of how stars and planets are born, because it does tie into this, but then we had too long of a talk. At times I will remind you, like, all that we just saw, those of you in the planetarium, about, things swirling together making planets. I'm going to show you examples of places in our galaxy where that's happening, but probably a few hundred to tens of thousands of solar systems forming all at once. So that's what we're going to be going after today. And it worked. Now, for these sorts of talks, I always kind of like to set the stage. For me, astronomy is all about perspective. That's what I tell my students. I study astronomy and I teach astronomy so that we can all get a nice, healthy dose of perspective, which is what the world needs more than ever. How many of you can recognize this picture? What are we looking at?
Santa Barbara.
Yes, Santa Barbara specifically. Where we are, right? Here we are, right here. This is the museum. I had to blink twice. This is so tucked away in the neighborhood that I was like, do I have the right location in the Google map? But I double checked. It is right. This is the bird's eye view, literally, and kind of where we're at. You can see the parking lots, the buildings, and then I like to kind of zoom out and sort of see the level of the city, and you can start to see some of the golf courses and playing fields and mountains and lovely environment that we have here. And then as we zoom out a little further, you can actually start to see this interesting piece of coastline that, according to this picture, runs exactly east-west, because that must be what happens in California. And there's this lovely range of mountains, and then the coast, and that's the geography here, right? Until we zoom out a little more, and we're like, oh wait, it kind of does a diagonal thing, and there's islands, and you can start to see our ocean, the inland deserts of Central Valley, and where I live, it turned out to be just off the eastern edge. I drove from there today, so you can see my entire drive today was sort of like this far, and it took 2.5 hours. All right? Up a little further, this would be like, higher than a satellite now, and you start to get the sense that the Earth is curved, and that the coastline is actually more north-south than east-west. And then finally, we see our whole planet as a lovely blue marble suspended in the dark. Okay, so just to get a sense that the Earth is, big, but also small. Okay, so I don't know if you have, like me, the iPhone has this cool, stock wallpaper screen you can put on. If you want to know how to activate it, I can show you later. And it shows literally where the planets are. I did this screenshot yesterday, but they haven't moved that much. So that's kind of cool. You can kind of tell where the planets are relative to each other. But you get a really warped idea of how close together they are, because they are not. Still, I cannot find a graphic I like better than this one from a textbook in 2005 that still includes Pluto as a planet, because it was 2005, and Pluto was demoted in 2006. This is still kind of my best scale model of the solar system. You can see, Jupiter's here, the asteroid belt, and then the inner planets that was, the planetarium show is telling us how maybe Jupiter is responsible for making the asteroid belt and the inner planets. But this is really the sense of scale. I mean, you can't see the actual planets, but the relative size of the orbits is correct. And if you were to scale this so that, Mars and all the inner planets' orbits fit on the face of a US quarter, Neptune would be a bicycle tire. Like, that's how spread out things are, just in our little solar system. And then the relative sizes of things too, it's kind of helpful to have them put next to each other. So it turns out that these are almost all of the terrestrial, rocky, icy, basically things you could walk on or maybe swim on. They have a solid surface, and they're massive enough that their gravity can shape them into a ball. This is almost a complete inventory. There's probably a couple far out things that we haven't discovered yet or that are missing. But Earth is the biggest of these, right? And then this is Venus without the clouds. This is Mars, and then wait, that's not a planet. That's not a planet. We know what these are, right? Ganymede, biggest moon of Jupiter. Titan, biggest of Saturn. Here's another planet, Mercury. Several more moons in this row, and then we get to Pluto, now considered a dwarf planet, and its moon Charon over here, also quite big. And note that Earth's moon is also really kind of a monster. It's one of the biggest moons in the solar system. Then there are asteroids. The biggest one and the first to be discovered, Ceres. So it's also big enough to be round. These are the relative sizes of the rocky terrestrial worlds in the solar system. Now let's jump up and compare the largest of them, Earth, to the big guys. Jupiter, the monster, with the great red spot, this swirling hurricane that's larger than our planet. Saturn, with its rings that are 100,000 kilometers from tip to tip. They're, make the planet look even bigger than it really is. Uranus and Neptune, now often called ice giants. Now, one interesting thing about our solar system, we think of the big division as being between the terrestrial, Earth-like worlds and maybe the Jovian gas giant worlds, right? But just as an aside, this isn't the purpose of my talk. People who study extrasolar planets are actually finding that if you look around other stars, the gap in size is not between Earth and Neptune. It's actually between Neptune-Uranus size things and Jupiter-Saturn size things. It's very odd. There seems to be a deficit of things in the galaxy, planets between the size of these two and these two. But there turn out to be lots of them that are between the sizes of these and the size of this. Why is that? Well, we don't really know. That's an area of active research, and it's not mine, but I think it's worth pointing out that our solar system is just one example, and even the wonderful detailed story, if you went to the planetarium show, if you delve too far deeply into the details of our solar system, you might just be telling the story of one, and you don't know how much that's, it's like saying your own life story is very important to you, but how much does it inform other people's life stories? It may be different. Okay, so these are planets. I mostly want to talk about stars. So this is just to set us up for the idea of like, stars are big, okay? Here's the sun, and here's the previous picture to scale, okay? And by the way, here's the Earth and the Moon distance. I don't know if you realize this, but the distance from the Earth to the Moon is considerably less, 384,000 kilometers, than the diameter of the sun, which is almost 1.4 million kilometers. Right? And the sun contains 99% of the mass, the stuff in the solar system. 99% is just the sun, and half of what's left is just Jupiter. Okay, and then Saturn and everything, all the other things I showed you, and all the smaller stuff that I didn't add that all up, that you get the remaining 1/2 of 1% of the solar system by mass. Okay, you may have heard sometime that the sun is like an average yellow star. I had a student ask me the other day, what does that mean? And I'm like, yeah, it really depends on what you mean by the word average and that how you would define that. But we do have different types of stars. Some of you may know the spectral typing sequence, especially those of you who are amateur astronomers. Some of you may not. We arrange them in a sequence. Usually we start here, O, B, A, F, G, K, M. It makes no sense. It's in its old system that was laid down before we knew what it meant. It had to do with features in the spectra that they sorted by like how strong the features were, and then realized that if you put them in a sensible order, which is this one, whereas as you go from left to right here, you get stars that are hotter, more massive, more luminous, meaning higher wattage, and shorter lifetimes. This is the sequence. To remember this, I think the people my age and older in the room will remember something like, oh, be a fine girl, kiss me, or if you prefer, be a fine guy, kiss me. My students prefer things that are less overtly kind of romantic seeming, so one of my students gave me this, oh boy, a fat gorilla kicked me. That one is unoffensive, so that's fine, we can go with that. In my talk today, now, so the sun, where does it lie? It's a G, so there's a sun. Okay, no point putting the planets and stuff here, they just be little specks. Most of my talk today is going to focus on the big ones, on the closest to me, the O's and the B's, the so-called high-mass stars. I'll put some numbers on this for you, for those of you who like numbers. Sun's surface temperature is about 5,800 degrees Kelvin. You can replace that with Celsius, it doesn't really matter. Fahrenheit, forget about it, this is science, sorry. It's a big number, right? The B stars, we're talking 20 to 30, 20,000, 25. O stars, 25 up to 50,000 degrees surface temperature. Masses, the sun is 1. A B star can be 10. An O star can be 30, 50, or even 100 times the mass of the sun. But where it's really impressive is the luminosity. Again, the sun is 1. Just think about all the light that the sun puts out is 1. One of these B stars is several tens of thousands of the sun in terms of power output. The O stars, several 100,000, and at the top end, 1 million suns outputting just one star. That's what we're talking with here. The diversity of properties among stars is amazing, and people who don't study it don't really appreciate that there can be that many different kinds of stars out there. But this prodigious power output of these O and B stars comes at a cost. They burn through their fuel faster than a Bugatti Chiron on the Nürburgring in Germany. This is this car that can go 250 miles per hour, but it basically, blows a gallon of gas out of its tailpipe every like 5 minutes or something. So they don't live very long. The sun can shine for 10 billion years. A B star, if you saw the video, the little sparklers going off, those were like the O and the B stars exploding. 20 million years, maybe. O stars, some of them only live 3 to 5 million years before they go boom. When the stars are born, they tend to be found in clusters. This is one of my favorite things to study. This is a favorite. You can probably see it in the sky if you go out late enough tonight. The Pleiades has some blue stars dominating it. It used to have O stars. They're gone. These are actually B or A type stars at this point. Their O stars already died in the Pleiades, but there are enough hot blue stars left to give it its bluish color. And then, of course, a favorite of any astronomer, the Great Nebula in Orion, is a much younger stellar nursery. Orion is only 1 to 2 million years old, so it still has O-stars, and they're still alive. The most luminous star is like 50 solar masses or something. Theta Orion, 30 or 50 solar masses. On the right, you have this classic picture from the Hubble Space Telescope, but I added on the left a picture I took, which I know some of you could probably do better. I took this with my digital camera attached to one of our 10-inch Meade telescopes that we have at Cal Poly. And I show this just because you can see those 4 stars in it, right? They're kind of hidden in the glare in the Hubble picture. But you see the 4 stars here? They're called a trapezium because that's what English people call a trapezoid. Right? And that's the shape, right? They look like a little trapezoid shape when you look at them, okay? Those are O and B type stars. Those are massive stars. And let this sink in for a minute. This whole beautiful nebula that you can see with the naked eye is lit up basically just by those 4 stars. Nothing else matters. There are more than 2,000 stars in this nebula, but only these 4. Okay, to be fair, most of those are actually binary triples, so it's actually more like 8 or 9 stars. But they're all massive. They're the ones that light up the nebula. The lower mass stars that are definitely forming in there, like the sun, and the baby solar systems, there are 2,000 baby solar systems in this nebula. They do basically nothing to light it up because they're so dim compared to these O stars. Okay, so here I actually have a movie that I don't know if I can get to play. I will try to click it, but if not, I might need Maria to help me, okay? Yes, I'll just let you do that. So we're going to start inside the Carina Nebula and see some of these beautiful pillars. And if you look carefully at these little fire hoses coming out, those are like those are material being ejected from baby solar systems that are forming in these pillars. Right? Okay, so let's play this video, and it's going to zoom out to show the full Hubble image, and it's going to zoom out again and show the whole nebula in a beautiful amateur astronomy image. Now we're going to shift into the infrared and see how the dust lanes disappear and reveal the stars and gas glowing within. Further into the infrared, we can see all these cold, cool clouds that are giving birth to the new stars. And then at the very end, if I didn't show you this coming out, you would be like, is this really the same thing? It is, trust me. This is an X-ray image of the Carina Nebula. And it's one that I was involved with producing, and I was at the press release in 2011 when this image was put out onto the world. This was my colleague Lisa Townsley's work. And Lisa actually passed away last year, so I always try to honor her contributions. And I show you this because in this image there's a lot going on. There's some crazy glowing like bat wing thing happening. This is actually there's actually 10 million degrees superheated plasma produced by the massive stars and their supernovae filling this region. But also, all these little dots you see up here, like bunch of dots, bright dot, bunch of dots everywhere. You know what those are? Baby stars. All of them. And there's 10,000 of them in this image. This is one nebula. It's a southern hemisphere object, so if you've ever had the privilege of going to Australia, Argentina, South Africa, and observe there, you can see this with the naked eye. Every one of these dots, well, some of these dots are massive O and B stars, about 200 of them, but the rest are like baby solar systems. And the solar flares that the video was talking about, running the risk of baking the Earth and getting rid of the oceans, that is exactly what's producing the detectable X-rays in an image like this. And quite a bit of my work is cataloging these sorts of baby stars and seeing how many of them are there. And in this particular nebula, we found 10,000 detected, but we can infer the presence of 40 to 50,000 just based on the fact that we don't expect to detect them all. Right? So in one nebula with 3 giant star clusters and several dozen smaller star clusters, I can tell you from my work that over the last 5 to 10 million years, this region has produced 40 to 50,000 baby solar systems that are still forming, could be forming planets right now. Every single one of these dots could be a future solar system, which is kind of what motivates me to study this stuff, because it's really fun to think about that. one more time just to, this is obviously not our galaxy, right? We can't take a picture of our galaxy like this because we're inside it. But, we think our galaxy might look something like this one. This is the Pinwheel Galaxy. It's another lovely telescope target because it's a face-on galaxy with nice spiral. And I show you this because you can see in it these dark things in the arms. These are the dust lanes. This is the coal, gas, and dust that gives birth to new stars. All these little sort of pinkish pearls are the ionized nebulae, like the Orion Nebula or the Carina Nebula. And all of these blue smears are the hot, probably B and A-type stars, some O-type stars that have emerged from those nebulae to shine for a few million years before they die out. When you see a galaxy like this, these are hallmarks of ongoing star birth. And star birth is what keeps a galaxy replenished and refreshed. It's alive. So I say that measuring the level of star formation activity of a galaxy is like taking its pulse. Right? Galaxies that aren't forming stars anymore, it's like they're dead. Galaxies that are forming lots of stars are very vigorous and alive, and they have a healthy pulse. Okay. So just keep in mind, I'm going to show you a video of this now switching, that every little glowing orb here is going to be something like the Carina Nebula, something that contains 50 to 100,000 baby stars. The Orion Nebula would be maybe one of the dimmest little things you could see here. It turns out Orion is not a super bright star-forming region in the galactic context. Okay, Maria, this is the one other movie. Oops, I've got to go back somehow. There we go, yeah, this is a movie. We'll just watch this. I did not make this one, I made the last one. This one is nice though, it's from it. Oh, it's not playing. Oh. There we go, thank you. So this is going to shift again from visible light to infrared. And look at all these beautiful little red jewels popping out. These are the very young star clusters. This is the X-ray stuff, like just like all throughout the galaxy, all these supernovas and other things that make the X-rays. And then this is putting it all together. So it would be like, that sequence I showed of the Carina Nebula, but now they're looking at all of those and some other galaxies stacked together in one picture. So I thought this was pretty cool. So I put it in my talk. And so our task now is to say, well, this is great. I mean, we can look at other galaxies. We can get a sense that there's star birth happening everywhere. But the problem is, the one picture you will never see in this galaxy is the one I showed you with the 10,000 little X-ray stars. Because we can't. We don't have the technology to see the stars in another galaxy. In our galaxy, we can sort of map out smaller nebulae. We can find where they are. We can look deeper inside them and find the stars and learn a lot more about what's going on. That's basically what I do for my research. Right? But I want to focus more on, for this talk, not the stars, finding all the stars, but finding various star-forming nebulae, and particularly interesting cases of O and B type massive stars that can teach us things about their properties and where they are in the galaxy. And this brings me to the main part of the talk, the citizen science. There's two science topics here. The first one is the shorter, the second one is the ongoing one that I'll tell a little more about. But the first talk is bubbles and star birth. Okay? So, but as a matter of introduction, I don't know, how many of you have ever heard of the Zooniverse? Okay, great. The fact that there's only a few hands means I'm doing a public service. So if you have a phone, please feel free to snap this, okay? It will take you to this website, zooniverse.org, where there are over 100 active projects across all fields of science and many non-science fields, like history projects, there's biology, there's linguistic things. I chose to just show the space stuff for this screenshot, but they have a lot more. You can get involved in any one of these that you want, like tonight or tomorrow if you want, if you go to this site. This is an opportunity for you to contribute to real science that real scientists care about and that ultimately gets published. I've been involved in a couple of Zooniverse projects since kind of the beginning. I actually know the people who came up with this whole thing. They're based in England. Okay? And so what I'm going to be talking about is sort of my projects within the Zooniverse, but I want you to go do whatever project you want. You don't need to do mine or just mine. There's a lot of other stuff you can do, and it's all great. Just be aware that for these sorts of Zooniverse QR codes, you go there, you can snap on your phone, but most of these work better on a computer than on a phone. So you might want to forward the website along to your computer instead of trying to do it on your phone. For most of these, it will work better on a real computer. Okay, so here's the basic science. I want you to imagine a candle. Okay, I put numbers on this earlier. I just want to kind of give you an analogy. So the candle is a low-mass star like the sun. It gives out a nice, somewhat steady yellow, warming light for a decent amount of time, before it burns out. So if the sun's light output is, if the candle is like the sun putting out light, then the O and B massive stars are kind of like the fireworks in the stadium. Boom, there's a bunch, and they're really bright and they're spectacular, and then they're gone. So think of that. So this is about sort of the light output and how long does it last. But there's more. I mean, you've probably heard of the solar wind, right? The sun puts out this stream of particles. It creates aurorae, which can be very pretty, although not often seen in California. It puts out space weather. Solar flares can be dangerous to astronauts. They can cause us to shut down satellites and things like that. The solar wind actually travels outward from the sun. It speeds it anywhere from 300 to 700 kilometers per second. And the sun is always kind of on a weight loss program due to this wind. Nevertheless, in our context, we'll consider the wind of the sun to be just kind of a steady zephyr, not too bad. Massive stars have winds as well. They're more like hurricane. A high mass star has a wind that can travel at 1,500 to 2,000 kilometers per second, so 3 times faster than the solar wind. And the windiest massive stars have been observed to lose the equivalent weight of all of our sun in as little as 10,000 years, which is not long. Imagine if our sun lost all of its mass in 10,000 years, or even a million years. A more typical massive star would shed the equivalent mass of our sun in about 1 million years, or maybe 10 million. But if the sun did that, the sun would have evaporated before Earth formed. Like, there'd be no sun. So it's actually kind of an important thing that people don't think about a lot. And the impacts of these winds and this light radiation from stars are felt widely. One of the first impacts is that these high-mass stars blow bubbles in space. They're windy. They inflate these bubbles. Analogy to kind of like soap bubbles. So inside here doesn't look like there's bright stars, but some of these stars evidently are windy enough to blow out a bubble. Okay? This is an infrared picture, so the stars are not that bright, but the dust is. The infrared tends to highlight the dust more than the stars. And so it turns out that when we see these telltale ring signatures, maybe with a glowing red center of a bubble, we may have just found a new star cluster with some massive stars in it, a newly discovered site of star birth in our galaxy. So we've set about surveying these over the years. It's actually been about 15 years or more, almost 20 since I first started doing this. And the most recent version of this survey was done via the Milky Way project. Actually, we did this several times. We started in 2010. There have been over 200 to 300 projects on the Zooniverse. Ours was, I think, the 10th project ever in the history of the Zooniverse. We were one of the originals. And this project is actually finished, so this is not one I'm asking you to help with. We got all our data, I'm showing you the results. But what we would do is, we would prepare an image. Actually, I prepared these myself. I prepared tens of thousands of them, little postage stamp images of our galaxy from surveys, and would just serve it up as random and ask people, do you see something in there? If you see a bubble, draw an oval around it. If you see a bow shock, draw this thing. If you see a star, and some other objects. This one doesn't have any bubble in it. It has a little bow shock, which I'll talk about next, that somebody identified in here. And we build this up on the website, and people go and they click and they make drawings, and we record those drawings and analyze them on the backside. This part of this project was engineered by my former student Harinder Jayasinghe, one of the most gifted undergraduates I've ever encountered. He was actually in the picture with me at the beginning of it that was taken from the newspaper you dug up. He graduated from Cal Poly in 2017, got his Ph.D. in 5 short years, and is now a prestigious Hubble postdoctoral fellow up in the Bay Area. So he is actually one of the most productive young astronomers of his generation, it turns out. He was an international student from Sri Lanka who transferred to Cal Poly as a junior, and then graduated in 2017 as the valedictorian of our entire college, like the whole College of Science, not just the Department of Physics. We don't usually get valedictorians from physics. We actually had one last year. It was amazing. She's at USC now, because we grade hard. It's hard to get straight A's in our department. But Turindo actually built the software backend to analyze everything I'm going to be presenting here, and was the lead author of the paper. And he went on to lead another Zooniverse project, which is still there. You may find on the site. It's called Citizen Assassin. He's the principal scientist of that project, which is another one that I would say check. It's about variable stars, which if you're an amateur astronomer, you have to love variable stars, because like amateurs give us so much monitoring of variable stars. And then I had a couple younger students, Jose and Lepore, who assisted us in testing things out. You can see them in our lab, right, with different screenshots of the project and things like that. Okay? And so the way this ended up working was we deployed it out to the world over a number of years. We gathered data, and this is just one little segment, a reconstructed area of the galaxy. All of these little white things are like all of the different bubble drawings that 70,000 people around the world made looking at our data set, just kind of all put together. And then Turindo's algorithm is able to find patterns in these and group them together into these sort of orange and cyan, what we call clusters, where, because sometimes people just draw whatever and we ignore that. Like this one by itself is nothing. It was the figment of someone's imagination. So it's democracy. If you're the only one voting for it, it doesn't get included. And then sort of some careful as we can averaging of all of the circles in these groups, we can come up with single ellipses and rings to identify, in most cases, real structures. In a couple of cases, maybe the same structure was sort of sliced up more than one way, because it's difficult to know how to count these things. So from this work, Turindo and our team, we published this catalog of 2,500 candidate star-forming bubbles throughout our galaxy. And about 1,400 of those we gave this category. Like, these are extra good. Like, we definitely trust those more than the rest, but so this was published back in 2019 for the Milky Way project. And so every one of these is something that I could go back and study when in my copious time, which I don't have, but they're sitting there, and it would be fun to go back and look inside these rings and see if we could find like the stars, for example. That's one thing we can do now. All right, so now the second, final, and kind of primary science now, this is our ongoing project, which is our current National Science Foundation grant is supporting this, is infrared bow shocks, and more about the winds of massive stars. Okay. So this is what we call the prototypical infrared bow shock. It's a beautiful O-star moving through space with this wispy arc dust around it. And it's our favorite because it just so happens to be the closest one to the sun, so we have the best picture of it. Most of them are very far away. This is such an iconic picture that I have it on my phone. You can literally go on the internet and buy a phone case with this, so that's kind of cool. But what's going on here, really? Why do we call it bow shock? Some people call them bow shock, by the way, because of the sort of shape of a bow, like a bow and arrow. I tend to like bow shocks because I'm a nautical person. That's probably why I like Santa Barbara so much. I love the harbor and the marina and stuff. So think bow as in bow wave of a ship moving across the sea. This is the analogy that my students and I like to use. So the arc-shaped nebula here, this is actually dust, but there's gas and dust that gets swept up in front of this star, like the wave of the ship. Now, the ship, it turns out, is not the star. The ship is the wind of the star. The ship is the flow of material coming off the star that then sweeps up material surrounding the star into this. Where is the star, you might ask? Well, it's simple. The star is the engine of the ship that's driving everything. So as the star puts out a wind in all directions, if the star is moving relative to the surrounding dust and gas in space, in the direction it's moving, it can pick up this stuff into a bow wave, and this is what we're seeing. And we tend to find that these stars need to be moving at least 10 kilometers, and maybe as many as 100 kilometers per second relative to the surrounding gas and dust to make this feature. If they're moving less than that, or if there's kind of a really dark, cold cloud around the star, we tend to not see a bow shock, we see a bubble. So bubbles and bow shocks are cousins. But the bow shocks happen when the star is moving quickly. Too quickly to sort of, it's moving so quickly that it would like escape from its own bubble in a way. So I have a colleague who's a professor at the University of Wyoming who years ago approached me and said, we were sort of two of the three people in the world who had published papers on these sort of objects before. We were kind of members of the same collaboration. The third group was some European group, and their work is great, but we didn't know them. So we teamed up with each other and said, there must be more of these. Like we had known, I'd found like 6 in a paper. He'd found like 10 more. The European group found another, 10 or 12. Like, well, these must be everywhere. Let's do a systematic search for these things. And so we did. We started a search with a team of students, including my former student Zulu. They've seen here winning the Cal statewide research competition for his presentation of this work in Bakersfield in 2016. And another group of students seen here at the 2-meter Wyoming Infrared Observatory Telescope in the summer of 2016, I believe. So my students, Don, Evan, and Daniel were involved in this. These other 2 students were from other schools. Okay, they were not actually directly involved in the bow shock work, but they were hanging out with the students who did. And this is a map of our galaxy, and every little triangle is like where one of these bow shock things were found in kind of the way we think it points. And they found 709 of them. And then a year later, when we compiled the Milky Way Project Citizen Science Catalog, we rediscovered half of this 709 and added 311 new ones. So we have over 1,000 now that we've cataloged throughout our galaxy. So one of the first that we noticed, Don, my student Don from the previous slide, he's now nearly finished his Ph.D. He actually spotted in the data the first kind of Milky Way Project identified bow shock from our latest thing, and it was in a neat location. I bet many of you know this picture. If you like astronomy, you know this picture. These are the famous pillars of creation in the Eagle Nebula. This Hubble image made it famous years ago, right? And now, of course, as of last year, we have a wonderful James Webb Space Telescope image where the pillars dissolve and reveal more of the stars inside, right? There's an interesting thing, though, that one of my students pointed out to me in this image. See this? Yeah, that's probably bow shock too. Although it's not one of ours. We couldn't find it in our data. You need to go into this data and look carefully. But we found some more that were close by to this. All right, so why are these pillars here? Again, massive stars, radiation and wind. There is a cluster of O and B type massive stars way up above the top of this, bathing these clouds in their winds and radiation and eroding them the way cliffs get eroded in Utah by the weather, right? But it turns out they're not the only massive stars in the neighborhood. There are more. But we need to zoom out to see this better. So I'm going to zoom out, and this is now Spitzer telescope, so it's a fuzzier image. It's a much smaller space telescope, but Spitzer was like our workhorse for this. And you'll see the pillars here, like the claw of the eagle pointing up. You see how that's pointing up here? You see that other pillar there pointing up the other way? Where they meet, right up here, is the cluster of the massive stars. Because that's sort of the source of the erosion, so they point back at it. But look down here. Boop, boop, boop. These little red halos, those are all fuzzy versions of the bow shock. They're just further away versions of this picture on my phone, so they look blurry and small. And what's interesting about them is their little arcs all kind of point back in the same direction, which implies that these ones, I don't think they're all like falling into the middle. That doesn't make sense to me. I think what's happening is that the same winds of this and radiation of the stars here that are coming out, sweeping past the pillars like a wave, they're coming out further and colliding with the winds of these other massive stars to make them have these little arcs that point back. Right? So this is a set that we discovered. It was part of the original 709 that the undergrads at Wyoming found as part of their summer project. We zoom out even further. Oh yeah, and here's of course, another James Webb image of the pillars for Halloween. Okay. We zoom out even further. Pillars are here. The other side of the Eagle Nebula is up here. 2 more that we found on the other side. So this nebula is littered with high mass stars. They're like all over the place, right? They're in the middle here, and they're also on the outside. But it turns out when you look at the image like this, you can't really see. But when you boost the contrast right, there's one up here too, in the upper right. This was our first bow shot found. This thing, almost off the edge. Do you see it? A little red arc. So that was one of the ones that the Milky Way Project volunteers found that was missed by the students who were searching nearby. I think they missed it because it was such a bright image. Is that a question? Or? Yeah.
What is the distance between the stars here you're talking about?
Yeah, great question. What is the distance between the stars here? So a big complex like this, all the way across, you're probably talking about 30 light years, or sorry, I think in parsecs. No, probably like 30 parsecs, so almost 100 light years across, like from here to here. Think of that. It's going to be 50 to 100 light years across, so it's big, quite big. Okay, so these are my current students, right? This is Angelica. She's actually responsible for the latest project for citizen science that I'm going to share with you that's currently active and you can work on. This is her in Seattle last year after presenting her work at the American Astronomical Society conference. They had some beautiful blown up pictures from the Webb telescope, so I had her pose next to one of these. These are some of our most recent summer students who went to Wyoming, and their task was to observe the stars, to get spectra of the stars and do a better job characterizing the stars that are creating the bow shots, to measure the temperature. Is it an O star? Is it a B star? Learning our properties. So my students are Dylan and William. This is Alex and Xander. They were from other schools, but they were part of the same program. There were 8 of them total, so there were 4 other students not in this picture. This picture was taken the night that I went with them to try to observe at the 2-meter wide-array telescope. And what they're posing with here is a blinking red light and an alarm on a control unit that is supposed to link the control computer with the actual telescope in the dome to tell it to do stuff, and it was not working. So those of you who play with telescopes know that very often things don't work, and we were not able to get this to work. They looked surprisingly happy. They weren't really that happy about this. They were just putting on a brave face. They had just called down to my collaborator, Chip, and saying like, Chip, what do we do? And he was like, well, I'm not really sure, but if you press the space bar, you can make the beeping stop. So we were happy about that at least, because the beeping was really annoying. It turned out, sadly, that a night earlier, the dome had been struck by lightning, and the electronics have been fried, which did not really surprise me because I was personally driving through the thunder sleet storm that did it on my way into Laramie the day before. So I was like, yeah, that weather was pretty bad. I hope the telescope's going to be okay. And it wasn't, and they're still trying to fix it. So we didn't get as much data last summer as we would have liked, but they got some though, and so these students are working to prepare presentations for the next version of this meeting, which will be in New Orleans this January. So we'll be going there to present this work. But I want to really focus on Angelica's work because it's quite fantastic. She started working with me as only a sophomore, and she really is one of the most talented students I've had work for me in a while. She's made a lot of progress, and any things that have not been progress have probably not been her fault. It's just been either my fault or the vagaries of data. So here's the thing. So the slides I'm going to show now are actually Angelica made. She presented these at our campus in the spring. So the problem, stars lose mass through their winds, especially the massive stars. This I've mentioned. And as you can imagine, stars with stronger winds are going to lose more mass. And it matters to the whole life cycle of a star. What kind of mass are they going to end up with at the end of their life? What kind of supernova are they going to make? Are they going to leave behind a black hole or a neutron star? Right? That might matter depending on how much mass loss they did. What kind of a bubble are they going to blow? I mean, this idea of energy that stars inject back into galaxies through their winds is actually a pretty big deal in lots of areas of astrophysics right now. And so here's some examples of bow shock nebulae that we put into our site. Angelica made these. In every case, we put a cross on what we think is the star responsible, and you can sort of see we've oriented the images. So, I mean, they're not really like this, but I tried to orient them so they all faced up, so they could be measured in sort of a consistent way. So this is just an example of a few different varieties of stellar bow shock nebulae. And then the idea is we can actually measure the shapes and sizes of these bow shocks using like simple things like drawing a couple lines and a circle. And what we're really after is this parameter called the standoff distance. It's labeled as R0. It's the distance of the kind of middle close bit of the arc from the star. And why this matters is it kind of makes sense. If the star has a stronger wind, it's going to push the shock front further out. If it has a weaker wind, it's going to be closer in. And so we have a set of formulae that we can employ based on whether the shock front is far away or close in to tell us what is the strength of the wind from the star. And it turns out that this is a very hard thing to measure. Astronomers have multiple ways of doing this historically. There have been 3 or 4 different ways. Radio, X-ray, ultraviolet observations will do it. And they've always disagreed with each other. And not a little bit, but by a horrible, embarrassing amount, like factors of 10. And so we've come up with our own method that isn't necessarily better than any of the others, but it has completely different assumptions. So, if we get a similar answer, we might, even if ours is uncertain by factors of 2 or 5, at least it's different, and we can shed some light on the problem. So that's what we've been working towards. But we do need to know things like how far away is it, and that comes into what's the shape of the bow shock, what's the orientation of the bow shock, what's the distance of the bow shock from the sun. The good news is we can get that from the star in most cases. We can do parallaxes for the star and do it that way to know how far away it is. But we're trying to measure the shapes and sizes, and that's where we're getting people. Mainly students in my classes have been doing this, but I will definitely invite any of you to participate if you like. You will not find this project on the Zooniverse site. You won't. It's built with the Zooniverse tools, but I did not make it a public site for the simple reason that it's not that many images. When I did the public Milky Way project, it was like 50,000 images. This is about 1,100. So we simply don't need that many people to do it, and there's a whole rigmarole to get published as a big Zooniverse site. So instead, think of the main Zooniverse as like, the thriving restaurants in downtown where lots of people go and they have fun and they hang out. Ours is like the little nightclub with the purple light over the door in the back alley that if I give you this passcode and the secret handshake, you can come in, but you have to know the link to go and use this. So I only share this with people that I present to or students in my classes, right? So, but please, you're welcome to come and help us. We're actually almost done. If we get a few more people coming in and measuring things, I think Angelica will have all the data she needs for her paper. So that's why I'm encouraging you to do this. So if you go to our site, I'll give you the QR code in just a minute because my talk is almost over. You will be presented with an interface that looks like this. It's pretty simple. It's going to show you one of these images where the star marked, and with some fuzzy thing like a bow shock, it's going to ask you to draw a rectangle to measure the sort of height and width of the bow shock. It's going to ask you to try to model this with a circle, and then at the end, if you think, oh, that was pretty fuzzy, that was didn't look right at all, and I don't like my drawings, it will ask you a question. How confident do you feel in your measurements? And you can say yes or not really. And that's really important because some of these actually don't look that great. It's real data. And the not reallys, Angelica, with enough people vote them down, she will just kind of put those to the side and only analyze the ones where people say, yes, this is good. We want that one. Angelica has made a lovely tutorial, which you go to the site, you can click the tutorial and go step by step. It tells you exactly what you need to do and all the background information. And here's the QR code. Again, you can scan it with a phone, but then send the link to your computer, because it's really, really hard to draw these rectangles and circles using not a mouse. It doesn't work so great. And the good news is we do have some results. Angelica has adapted the codes that Tarindu wrote to grab the existing data and analyze the shape parameters. Here's a plot of actual data. You don't need to care about the details, except look, each of these bow shocks has at least 6 and maybe more than 20 measurements, and she's sort of averaged the measurements to put them on these plots, so now every single dot represents a bow shock. And kind of the interesting thing about this is that, at least according to theory, not a super well-established theory, but the only one we have for these things, is the ones in the white region should be hyperbola shaped. They should be more open. And then the ones in the gray regions should be more closed. So if that's borne out, we might be able to investigate, is there something different about the stars or their motion for the dots to fall in the white, more open region versus the gray, more closed region. So that's something we haven't really looked at before. So I'm excited to see whether we can pull something out of this that's interesting. Okay, so that actually brings me to the end. I've talked enough. I would love it if you ask me questions. And it doesn't have to be about this, it can be about anything astronomy related. This is my sign off. I think there was a microphone trying to see the lady in the red shirt had a question.
Yes, is it on?
I can hear you.
Okay. I would think that the appearance of the bow shock would depend on the angle that the star is traveling, that we'd only see the component that is orthogonal to us. So how do we measure that angle of direction? Probably in part by Doppler shift, or will it be?
What a great question. Yeah, what a great question. Thank you. Yes, so that's actually something that I decided to gloss over for the sake of simplicity and the fact that it is actually one of our goals to maybe get a sense of the angle of this thing, but I'm becoming pessimistic about our ability to do that, just because it's science and things don't always work the way you'd like. There is an idea that sort of based on the going to the plot at the end here with these parameters, being able to kind of pull the dots here and assign them to some shape family, then you can sort of figure out, well, then based on what it looks like, this is how it's tilted on the sky. The idea here, folks, if you're wondering, is when Angelica presents this, I tell her to bring a prop or something. Like I should have an umbrella. That's a good model. Like imagine I'm holding an umbrella. If I hold the umbrella sideways, you can clearly see that it has a shape like one of these things, right? But if I held it this way, you wouldn't see the umbrella as an arc. You'd see it as just kind of a fuzz. And probably some of these are coming towards or away from us, and they wouldn't be in our catalog because there actually are things in the galaxy that sort of look like a star surrounded by fuzz. Some of them could be these that are heading towards us or away from us, but we don't catalog those because they don't have this shape. We think that it needs to be certainly within 45 degrees of the sky to even show up as something like this. Now your idea of, say, using a Doppler shift to get an idea of is the star coming towards us or away from us is a really good one. Problem is we don't have really any of these have good enough measurements of that for this to work. It turns out we have better measures of the motion of the stars across the sky now than we do towards or away from us. But even that's complicated because the bow shock is sensitive to the motion of the star relative to the gas and dust. And everything in our galaxy is moving like a psychotic carousel. And it's really hard to know which way things are supposed to be moving and figuring this out. So, for the time being, we're just having to kind of assume that they should be within 45 degrees of the sky, and we can put in a little correction factor for that, and that's the best we've been able to do so far.
Question. That doesn't seem like the microphone's on here. Anyway, the question is, you showed a image of different bow shocks in different directions, and did there seem to be any correlation with the arms of the Milky Way Galaxy, those different directions?
Oh yeah, you're probably talking about, if I can get back to it, the one with like all the little arrows. Oh, way back over here. Too many slides ago.
Yeah.
Come on. This one, right?
Yeah.
Yeah, so, this is really interesting. So, of course, one of the hardest things about being in our galaxy is it just looks like this, and we think there should be spiral arms. There's evidence for spiral arms. There's still debate about, what are our arms, where are they, how many are there, what would our galaxy look like. In fact, last week, I was in Pasadena at a conference called Surveying the Milky Way, the universe in our backyard, and even after a whole week of hearing experts on looking at the Milky Way talk, like for several hours a day on different things, and I gave my own presentation last Friday, we still don't know exactly what the configuration is. For the bow shocks, we don't really see any preferred direction. They're kind of all over the place in terms of which way they're pointing. Now you might ask, well, do you see an enhancement of them in directions that could be related to spiral arms? And the answer is, maybe, but it's hard to say. Like this little purple cluster here, like there may be a spiral arm there, right? But then there's sort of a spiral arm maybe going across this part of the galaxy here, and there's bow shocks everywhere. In fact, some work that one of my other collaborators did, another collaboration I'm in, found that there's sort of this idea of a spiral arm that goes through here. We call it the Sagittarius Carina arm, and it turns out that it's not really there. It's pitched out. All the star-forming regions sort of from here, definitely, here-ish, all the way to here. All of this stuff, where you would think if it's an arm, it's kind of should be going this way, it's really more like this. So now we think it's a spur, like an interruption, which we can sort of see a third dimension effect there. So it's actually a mess, and it's hard to tell that from these objects. One of the things that was a big surprise to us, I will say, when we, especially, so this is sort of the inner part of our galaxy. This is further out in the galaxy, so things here are a little more puffed out. But we were expecting that many of these bow shocks should be associated with what's called runaway stars. We were thinking they should be moving 30, 50 kilometers per second, like really fast to be making the bow shocks. Now, the first thing we noticed, of course, is fast-moving stars, they don't tend to stay confined just to the central plane of our galaxy. They should be a lot more up and down, right? And you notice the main feature of this is it's really flat. Like it's very confined to the middle of the galaxy. And if they're fast movers, they should be flying up and down. Now, initially we thought, well, maybe the issue is there are stars that run away, but if they run too far away, they've left the dust, and so there's nothing to light up anymore, and it won't make a shock. That was my first reaction when I saw this. But then my colleagues started measuring the motions of these stars, and they realized that they weren't moving fast enough. Rather than most of them moving 30 kilometers per second, more of them were moving like 10 or 11, which is actually just not fast enough to be runaway. So we think of them now as maybe walk away, like they kind of gradually drifted out of their birth clusters, but they didn't get flung out. And another thing that supports that is a surprising fraction of the bow shock driving stars are in binaries. Now the reason that's interesting is that if you have a fast-moving star, usually the way to do that is, it starts out of a binary system and something disrupts it. So it's like you whirl around two things on a string, you cut the string, right? What happens? They fly apart, but then they're not together anymore. We weren't really expecting to see many of the bow shocks in binaries. It turns out that at least a quarter of them are, so there were surprises here. does not have to be about the content of my talk. I am an all-purpose astronomy teacher.
What happened to that interesting building that you said is no longer there?
Oh yeah, what happened to the CLA building? Was built on a not discovered earthquake fault, and was condemned and had to be taken down. Yes, I know. Not only did we lose an icon, but money must have been expended to deconstruct this rather nice-looking building. And meanwhile, I'm still teaching in overcrowded classrooms. So I'm sure it'd be nice if we could build another building somewhere. They did build a building to replace it, but they filled it with administrators, not classroom space. So we're still waiting to get more room for ourselves and our students.
How many citizen scientists have participated?
Oh, quick on the right. Question in front is how many citizen scientists have participated. So in the Milky Way project, sort of classic over the years, I think we tabulated this in Turindu's paper. It was like 70,000 across in about 200 countries around the world. In this most current one that Angelica and I are running mostly off of students and presentations like this, we've had probably 200 people participate. And that's actually been enough. Oh, we'll go to the back here and then.
Yeah, you mentioned a screensaver for the iPhone that shows the real-time solar system.
Yep.
And you promised to tell us where the link was.
Oh, yeah. Well, if you have an iPhone and it has to be just, it's on my phone, just has to be the latest version. All you need to do is on your home screen and you tap it, you hold it. If I can get this to work. Oh, I think I have to look at it for that to happen. And then if you press while you're looking at it, it will let you go into these choosing different screens. So like, here's my children, here's the solar system, here's real time. This one's fun too, location on the Earth, where you are. So if you tap that, it shows we're in California, it's night. And there's this plus sign. So once you tap that, you can unlock. It's just built into the operating system now on all the iPhones. I mean, it has to be one of the later versions, but if you have it, the key is while you're staring at it, you press and hold the screen rather than swipe and unlock it, and it brings you to this little page left and right thing. And I promise, if you have any younger people in your life, children, grandchildren, nieces, nephews, they will show you how to do this. They know. I think they're the ones who showed me.
Just going back to the building that was gone. It looks reminiscent of some of the astronomical instruments in like Tashkent or in India. Was it meant to mimic some of those?
I highly doubt it.
Okay.
I think it was built before my time at Cal Poly, but when it was built, Cal Poly had a department of physics. The and astronomy was added later, so I don't think my school did very much with astronomy in mind in the old days. We do a lot more now. We have a question in the front.
How far away is the Leo constellation?
How far away is the Leo constellation? You stump me. Off the top of my head, I don't know. But most constellations, you can't really say the distance because all of the stars are in them are different distances away. So it would be, the answer is several different distances for all the different stars.
So, once you get all the data that you're hoping for, or whatever, what is the hope?
Once we get all the, you mean me personally?
Well, no, with the bow shots, right?
Yes.
As you learn more about this.
Yeah.
What is the hope?
So what we want to do ultimately is, for as many of them as possible, and it's not going to be all of them because they won't all have enough data, we want to measure their mass loss rates. We want to actually get a number. This star is shedding this many solar masses per year. And then we want to compare that to the measurements of the stars themselves that the students were doing with this telescope and others, and see the correlations. And we've actually already published a few papers like that. We're on our second, if you wouldn't believe, we're on our second round of National Science Foundation funding now. We already did a 3-year grant. We're now on our second 3-year grant to kind of do it over and do it better. And the main thing that's improving in this second grant is, again, we're trying to get these better ideas of the shapes and sizes of the bow shocks. But we have much better information about the stars, so we're hoping to pin it down. But there have already been some interesting trends, like, for example, the B-type stars. We have one of the largest samples now of B-type stars with measured mass loss rates, because most of the previous ones focused on the O-types, because those are the really big ones. And we found that the winds were maybe stronger than were expected. Of course, what's expected depends on which theoretician you talk to, because the one who predicted would say, of course, and the ones who predicted the other thing would say, rah, 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 right? So, but there's actually some evidence for interesting behaviors that might relate to the atmospheres of the stars, and so we're seeing some trends that are new and encouraging, and that's why we're keeping at it. Oh, yes.
So we're losing solar mass, and it's creating these bow waves. Is all that material creating somewhere, material for something else?
Yeah, it's all the material that the stars are shedding ending up somewhere else. And the answer is, yes, eventually. When it comes off the star, it's quite hot, so it may need to cool down quite a bit before it can be incorporated to something else. But the thing I should remind you, though, is, if you learned about, say, supernovae, the amount of mass that a star loses in terms of its wind is significant, but it's nothing compared to what it will lose when it explodes later. So in terms of mass, the winds of these stars are not going to be that important to the overall material budget of a galaxy. But in terms of energy, they are. They're more important for energy. So the fact that they sort of heat up and stir the other material around, that's their more important effect than whatever mass they lose. In fact, some calculations would say that the amount of energy that a star puts out over the course of its lifetime through its winds, and remember, this is energy that can actually move stuff around. It makes the bow waves, it makes the bubbles, it stirs up the galaxy. Could be the same amount of energy over the star's life as that star will then release all at once as a supernova. So it's kind of more spread out. But another interesting thing that happens, for example, the picture I showed of the Carina Nebula with the X-rays inside. Well, there actually is the case of the missing supernova in our galaxy, or I should say missing supernovas. We only seem to have observed about half as many supernova remnants, this is the debris left over from exploded stars, as we would expect there to be, given the amount of stars being born in our galaxy. And our thinking now is that because these stars are so windy, because they blow bubbles, and they stars form in clusters, that when the supernovae go off, a lot of them will go off inside these kind of echo chambers. They'll go off inside these empty bubbles, and so you won't really see the explosion. It's sort of like if you kind of threw a stick of dynamite down a well, and it's like just kind of echoes in there, and it doesn't create a big boom. So the effect of the winds and the radiation may be, in some cases, to hide the supernovae, and we're sort of seeing them come out now in some of these traces of the X-ray emission and things like that. Yeah, how many baby solar systems? That's a wonderful question, and it was supposed to be like the goal of my Ph.D. thesis to come up with that number. And I have to admit, I never personally came up with that number. I failed. What I did manage to do was team up with a colleague several years ago, and we kind of combed through the literature and all the different people who had tried to estimate that number over the past 40 years. And they had all come up with slightly different numbers, and then we were like, wait, but they all use sort of different key assumptions. And so then we recalculated all their numbers based on a consistent set of assumptions that are kind of in vogue now, like we think are, I don't know if they're right, but they're at least agreed upon. So based on it, and this is still cited, in fact, at the conference I was at this last week, they opened by citing the number that we came up with in 2011. And the answer is about 2 per year. Now, that's an average. Of course, it takes more. Rome wasn't built in a day, and the solar system isn't made in a year. But sort of, if you average it out, you get about the equivalent of 2 of our suns being born in our galaxy each year right now. So that's what we call the star formation rate, and that is what I would say is the pulse of our galaxy. And ultimately, the number of bubbles we find, and if we look at it carefully, should conform to that sort of number and, you know, kind of be another way of accessing it.
In passing, you seem to indicate that galaxies, I mean, we know stars age and they're born and die, but galaxies also.
Yes, galaxies do, and I did not include in my talk like slides showing the array of galaxies, but so he's just asking like, okay, how many solar systems are being born every year? And so we can say that there's 2 suns worth of mass being made into stars every year. So then what ends up happening, I'm going to have to run back a couple slides if I can. I think I can. I want to go back to that slide where I showed all the different kinds of stars. Right, so we're looking at a galaxy, and then, yeah, a whole galaxy like this. So again, a galaxy like this, you know, few solar masses worth being born every year. And in this galaxy, whoops, you know, the evidence for this is that you have all these blue stars. Okay, now, here's the thing. Remember what I said about blue stars? They're hot, they're bright, they don't live very long. So if you're going to see blue stars, it means they're being consistently replenished all the time. It also means that they'll explode as supernovae and they will return the material for future generations of star growth, if they're the massive stars. But there's a problem. Most of the stars in this galaxy, like I said, most of the stars in the Orion Nebula are not visible in a picture like this. They are not the hot blue stars. They are the cold yellow red stars like the sun. Whoops, right here. So when you look at a galaxy that's making stars, you see all the light from these big blue ones. But if that galaxy is consuming 2, 5, maybe 10 solar masses per year, what if that isn't, what happens to it next? It doesn't all get sent back. That's the problem. Most of it doesn't make, most of the mass does not go into stars like this. Most of the light comes from stars like this. Most of the mass goes into stars like the sun or less, because these stars outnumber these stars by 100 or 1,000 to 1. So the issue is, you know, I said the sun lives 10 billion years. These little ones live for hundreds of billion years. In fact, these little ones here, these so-called M dwarfs, they live for so long that no M dwarf star that has ever been born has ever died, because they live longer than the age of the universe so far. Okay? That mass that gets locked up into these teeming hordes of little orange and red dwarfs is lost to the galaxy. It's locked up into stars. It's great, maybe if there's any life forms living on planets around those stars, they would have hundreds of billions of years to potentially evolve. But the material from these stars does not get sent back to make any new stars. And so eventually, if you don't keep replenishing the gas in a galaxy from outside somehow, it will get used up. It will get expelled by all the supernovae. Maybe some of the winds, but mostly the supernova will blow it out. The rest is all locked up into these little orange and red dwarfs, and the galaxy loses its dust, becomes reddish-orange in color, and astronomers call these red and dead. Now, that's what we mean by a dead galaxy. It's only stars, and it's pretty much just these little dwarf stars. And there's red giants and stuff, because you know, stars like the sun that are in the process of dying. But there's no hot blue stars, there's no gas and dust left to make new ones. So that's what I meant by that.
Which one are we, A?
So we are this one. We're at G. G2, to be precise, yes. Sun is there. Yeah, the sun is, the sun's life cycle is a little bit less than the age of the universe. Right? The best guess age of the universe, about 13.7, 13.8 billion years. Sun's lifetime is 10. So there are stars the mass of the sun that formed very early in the universe that have now died. We are able to see remnants of dead sun-type stars, but we're not able to see remnants of dead M-dwarf stars. Even most K-type stars are still alive. These are long-lived. Oh, yeah. So I have one back there, and yeah. Yeah, so you're sort of asking like, yeah, the rate, so there's a couple, that's a great question, and I won't be able to answer it super well, because one thing we're finding is that the radius of curvature is a really hard thing to measure, because the bow shocks aren't actually circled. So this is kind of a theoretical prescription that was laid out by some theoreticians, not part of our groups. We're trying to use their formulation for this. And so we're finding that it's hard to choose how much of the arc to use to measure your circle, so I'm not trusting the circular radii super much right now. But the idea is that by itself, it doesn't tell us anything. It's only in comparison to like how far it is from the star and how wide it is. And some combinations of this can, using a certain model of geometry, can tell you something about the shape. And what that actually tells us about the physical properties is something we still want to investigate. It might have something to do with how strong the wind is of the star. It might have something to do with, one thing I'd like to investigate is whether there's a correlation with how fast the stars are moving, but we haven't quite done that yet. Like, we need to get actually the remaining measurements, and then we can compare things.
Well, that would be, if you had the, I guess it depends on the length of the experiment, or how much data you can collect over time. I was wondering if the variability of that circle in the bow shock could actually become a cycle.
Oh yeah, so yeah, you're asking if the bow shock images themselves change with time, and the answer is we don't have time data monitoring these, even the expectation of how quickly they could change in time. It ought to be pretty slow. The physical size of these things is several times larger than the solar system. So they're not going to be rapidly varying objects in any case, because there's sort of there'd be a time delay of months, if at least, for any signal to propagate across the length of one of these. But I mean, it would be amazing if we actually could see something like that, because you could probably learn about variability of the wind of the star, right? Like if the wind was gusting, you would expect to see the shock move in and out. We just don't have anything like the data to monitor these things over time. Maybe we should write a James Webb Telescope proposal to look at a few of these, and then go back a few years later and look at them and see if they changed. You know, be fun to do.
Just basic astronomy books you would recommend for an amateur to read?
Oh gosh.
I took a course in like 1982 or something, so
And you still remember about Doppler shifts and stuff. That's impressive. I wish my students in my class right now would remember Doppler shifts 40 years from now. Then I will have done my job. If they can come back to me in 40 years, if I'm still around, and say, I still remember Doppler shifts from your class, I would feel like I had done my work. There's just so many. There's so many books, and I think it's almost like, what specifically are you interested in learning about among it? I mean, I'm still a huge fan of some of the books by Carl Sagan. Those are classics, but there are more modern ones. Gosh, I just heard on the radio, a colleague from UCI has just published a book that I haven't even read, but I'm sure it's great because she's great. And it's like, it's about, she's someone who models planets around other stars, like what kinds of atmospheres they could have. I think she's got a book out about, like, you know, life on other planets or something. I think it's coming out right now. That's, you know, if you're interested in that sort of thing, that would probably be a really good read. Her name's Aomala Shields, professor from UC Irvine. But there's so many. There have been books on dark matter. There have been books on particle physics. There's all the stuff Neil deGrasse Tyson writes and things like that. Yeah, so maybe do you have a recommendation or a question? Yes?
So you said that a lot of these bow shocks have a lot of like this dust swirling out underneath them when they go over the universe. Theoretically, could smaller stars form from that dust?
Oh, what a cool question. Yeah. Could smaller stars form from the gas and dust in the bow shock? And the answer, sadly, is no. I can say pretty confidently that these objects don't have enough material in them to make other stars and planets, and they're also very likely too hot. Like, you need the gas and dust to be pretty cool so it can condense and make other worlds. In fact, one of the things I'm not sure we even understand super great now is whether the dust we see in the bow shock is really sitting there or whether it's actually getting destroyed and having to be replenished by being swept up, because dust is pretty fragile, so there's a chance that the dust is being evaporated or shattered even in the process of going through the shock. So sadly, no, I would not expect other planets and stars to form out of that material. Yeah, really good question. Oh, how many planets are in the Goldilocks zone? You mean in our galaxy? I just looking at an outdated book on this. So the Goldilocks zone, if you're not, in case you don't know, is like where Earth is, the so-called habitable zone. It's a planet where it's not too hot, not too cold. It's too hot, the water evaporates. It's too cold, it freezes. Just right, you can have liquid water, which we think is the prerequisite for life like us, because we're mostly water. The current finding, which I still think is one of the more exciting astronomy results of my lifetime, is that most, if not all, stars in our galaxy have planets. Now, what fraction of those stars have a planet in the Goldilocks zone? I believe that remains a bit of an open question. I mean, it's probably not all of them, but it's not a small enough amount to discount it. Right? It's probably at least 5 to 10%. One thing that people are interested in, though, is still figuring out what really is the Goldilocks zone. And again, we come back to my friends, the K and the M type stars. There's still raging debates among astronomers. And in fact, so I'm a stellar astronomer, and I specialize in really young stars, but I also specialize in X-ray emission. And so it turns out that these runty stars are ridiculously active and put out tons of X-ray and ultraviolet. This is a problem. For the same reason that the planetarium show said about the baby sun maybe putting out a harmful amount of X-rays, but a baby M star puts out that harmful amount of X-rays for much longer than the baby sun, because they do everything slower. And even worse, the Goldilocks zone of an M star has to hold its planets really close, because the star is so dim. It'd be like, okay, well, we orbit the sun, we're warming ourselves around a campfire, but try warming yourself around a candle. I mean, you can do it, but you gotta get really close to that candle. So any planets around the M dwarf stars, and there have been some, if you ever heard of like TRAPPIST-1 is an exciting system, like 7 planets and 3 or 4 are in the Goldilocks zone, but they're all like way closer into that star than the orbit of Mercury. And that becomes a problem when that star is putting out solar flares on steroids all the time. There's a serious issue about whether those stars could be sterilized by the high energy radiation. And so it's really hard to even answer the question right now, because it could be, well, what kind of star are you talking about? We live around this star. We kind of understand why this is okay for us. We think some fraction of these K stars are probably okay too. M stars, we're like, I don't know, tons of them are out there. They live forever. If it was a good place to live, it would be a good place to live for a long time. But maybe there'd be dragons, like that could be dangerous. And then F and A stars, well, sure, they can make planets, but they're gonna burn out. Like, if we lived around an F star, yeah, we probably maybe could have gotten to now-ish, depending on the star, before it burns out. Some of them would have maybe had long enough for, bacteria and stuff, not dinosaurs. Like, the star dies before like for these ones, forget about the big ones I've been talking about. For these ones, the star dies before like multicellular life on Earth evolves, so that's a problem. Right? So there's different ways of defining Goldilocks here. It's also like, what kind of star do you live around?
Oh, just to let people know, we'll have this program recorded and put on our YouTube channel. If you go to our website, sbau.org, you can look up the YouTube channel there, and you can see a recording of this if you want to pick out some more facts.
So I'm happy to chat with people afterwards. I think we don't want to hold everyone here. It's getting late. But thank you. You are a wonderful audience. Thank you very much. I would love to have you in my classroom.
Matthew S. Povich, you did good. We'd like to, on behalf of the club, Santa Barbara Astronomical Unit, present you with our priceless porcelain cup.
This is a great one.
Yeah, it's got our logo on there. Anytime you have a drink of coffee, you think of us.
I will.
And our honorarium, we give you a little gas on the way back.
Thank you so much.
And we thank you. We're going to have you back.
I will.
Bag too.
I thought if that was only because he wanted to turn down the check.
All right.